Hello everyone and welcome back to Wire and Wiki. Thanks for coming by to hang out with me while I make a thing and talk about stuff. What stuff are we talking about this week? We're going to talk about what the heck is a moodstone made of and what makes it work and change color. And then I fell down the rabbit hole. From mood ring to liquid crystal to thermochromism to liquid crystal thermometers to on and on and on, and we'll see what all we can talk about. We are working with a horse eye stone this episode, faceted, and I intended with this design to not have to try and get a wrap around the point at the bottom. And I succeeded, yay! It took a few tries to figure out how to do it so it wouldn't be toppling over when you try to wear it. You want it to lay flat and not jiggle around. And this one will do it. I don't recommend this wrap for any kind of stone that's clear. You don't want to see all that wire weaving through a clear stone. We'll tackle working on clear stones in a different episode, but this one works great for this particular stone. I started out looking up on Wikipedia about moon rings, and I was hoping that there would be some kind of explanation or story about the man that invented them back in the day. Back in the day, meaning the 60s and 70s. But it's really only just a few sentences. It says, mood ring. The mood ring is a finger ring that contains thermochromic element, or moodstone, that changes colors based on the temperature of the finger of the wearer. Finger temperature, as long as the ambient temperature is relatively constant, is significantly determined by peripheral blood flow, which is modulated by the autonomic nervous system. A mood ring contains liquid crystals which change color depending on the temperature. And that's all it has to say about it. Yeah, and I know there's a whole big story about it. It has a whole part of the culture in the 70s. So I don't know why it doesn't make any sense. Anyway, so in reading this, a mood ring is a finger ring that contains thermochromic element. I was like, oh, what the heck is a thermochromic element? Alright, well, we'll get to that. We will find out what a thermochromic element is. And the mood ring contains liquid crystals. Now, I've heard of liquid crystals. There's liquid crystal displays. Clocks and watches and whatnot. But what are they? I mean, it can't be a crystal that's liquid, right? Well, we're going to find out. So my second thought after seeing that this mood ring section was only a couple sentences was to look up liquid crystal thermometers. Because they're pretty much the same thing. They work the same way. The same sort of stuff in them. And there's really just a couple paragraphs about them. And it says, liquid crystal thermometer. A liquid crystal thermometer, temperature strip, or plastic strip thermometer is a type of thermometer that contains heat-sensitive, thermochromic, there's that word again, liquid crystals, there's that word again, and a plastic strip that change color to indicate different temperatures. Liquid crystals possess the mechanical properties of a liquid, but have the optical properties of a single crystal. Temperature change can affect the color of a liquid crystal, which makes them useful for temperature measurement. The resolution of a liquid crystal sensor is in the 0.1 Celsius to 0.2 Fahrenheit range. Disposable liquid crystal thermometers have been developed for home and medical use. For example, the thermometer is black and is put onto someone's forehead. It will change color depending on the temperature of the person. There are two stages in the liquid crystal. The hot nemetic stage is the closest to the liquid phase, where the molecules are freely moving around and only partly ordered, and the cold smectic stage is closest to a solid phase, where the molecules align themselves in a tightly wound chiral matrices. In researching this and reading forward about thermochromism and liquid crystals, they say pneumatic and smectic stage a lot. And pneumatic just means that the crystals arrange themselves one way when they're hot, and smectic just means they arrange themselves this other way when they're cold. And that's what causes the color change. And it goes on to say liquid crystal thermometers portray temperatures as colors and can be used to follow temperature changes caused by heat flow. They can be used to observe the heat flows by conduction, convection, and radiation. In medical applications, liquid crystal thermometers may be used to read body temperatures by placing them against the forehead. These are safer than the mercury in glass thermometers and may be advantageous in some patients, but do not always give an exact result, except for the analytic liquid crystal thermometer, which shows the exact temperature between 35.5 and 40.5 Celsius, that is 96 to 105 Fahrenheit. Liquid crystal thermometers are also commonly used in aquariums, in home brewing, and in mood rings. The liquid crystal thermometer was invented by Bob Parker in California, one of the many inventors' thermochromic applications patented in the 1970s. That's all that Wikipedia has to say about the thermometers, which really, there's a little bit of explaining in here how liquid crystal thermochromic blah 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 does its thing, but it wasn't really answering my question, so I clicked on thermochromic, or is it thermochromic? I don't know. Thermochromism. And it came over here and there's a picture of a mood ring on the page for thermochromism. And thermochromism says, thermochromism is the property of substances to change color due to a change in temperature. The mood ring is an excellent example of this phenomenon. But thermochromism also has more practical uses, such as baby bottles, which change to different colors when cool enough to drink, or kettles, which change when water is at or near a boiling point. Thermochromism is one of several types of chromism. I don't know that I'm going to read all the different types, but let's start here with thermochromatic liquid crystals. Two common approaches are based on liquid crystals and Leukodyes. Liquid crystals are used in precision applications as their responses can be engineered to accurate temperatures, but their color range is limited by the principle of operation. Leukodyes allow a wider range of colors to be used, but their response temperatures are more difficult to set with accuracy. So I'm guessing that this is a dye that you would put in the thermochromatic liquid crystals, and then when it changes to their direction, anyway, some liquid crystals are capable of displaying different colors at different temperatures. This change is dependent on selective reflection of certain wavelengths of the crystallic structure of the material, as it changes between the low temperature crystallic phase through the antistropic chiral or twisted nematic phase to the high temperature isotropic liquid phase. Only the nematic mesophase has thermochromic properties. This restricts the effective temperature range of the material. The twisted nematic phase has molecules oriented in layers with regular changing orientation, which gives them periodic spacing. The light passing through the crystal undergoes Bragg diffraction on these layers. The wavelength with the greatest constructive interference is reflected back, which is perceived as a spectral color. A change in the crystal temperature can result in a change of the spacing between the layers, and therefore the reflective wavelength. The color of the thermochromic liquid crystal can therefore continuously range from non-reflective, black, through the spectral colors to black again, depending on the temperature. Typically, the high temperature state will reflect blue-violet, and that's what happens with these moodstones that I have. When it's really warm, they're blue-violet, while the low temperature state will reflect red-orange, and that's what happens with these two. When you first pick them up, they turn orange, and then they go green, and then blue. But if they're just sitting on their own, they're anywhere from gray to a light champagne color. But anyway, while the low temperature state will reflect red-orange, since blue is a shorter wavelength than red, this indicates that the distance of layer spacing is reduced by heating through the liquid crystal state. Some such materials are cholesterol nanonoate, or cyanobiphenyls. But when they say cholesterol, they mean cholesterol, like you imagine cholesterol. But yeah, it can be used in for things other than clogging your arteries. Mixtures with a 3 to 5 centigrade span of temperature and ranges from about 17 to 23 centigrade to about 37 to 40 centigrade can be composed for varying proportions of cholesterol oleoyl carbonate, cholesterol cyanonanoate and cholesterol benzoate. For example, the mass ratio. Yeah, nobody's using that. Never mind. Liquid crystals used in dyes and inks often come microencapsulated in the form of suspension. Liquid crystals are used in applications where the color change has to be accurately defined. They find applications in thermometers for room, refrigerator, aquarium, and medical use, and indicators of the level of propane in tanks. That's true. I thought of that. A popular application of the thermochromic liquid crystals are mood rings. Liquid crystals are difficult to work with and require specialized printing equipment. The material itself is also typically more expensive than alternative technologies. High temperatures, ultraviolet radiation, some chemicals and/or solvents have a negative impact on their lifespan. Leukodyes. Thermochromatic dyes are based on mixtures of leukodyes with other suitable chemicals, displaying a color range, usually between the colorless leucoform and the colored form, that depends upon temperature. The dyes are rarely applied on materials directly. They are usually in the form of microcapsules with a mixture sealed inside. An illustrative example is the hypercolor fashion. Hypercolor fashion? Haven't thought about that in a while. I think they came out when I was in high school. The t-shirts that you show that your armpits are really hot. Anyway, and I've ruined quite a few by putting them through the dryer too many times. Yeah, they stopped working after a while. While microcapsules with crystal violet lactone, weak acid, and dissociable salt dissolved in dodecanol are applied to the fabric. Got that? We can make our own now. When the solvent is solid, the dye exists in its lactone leucoform, while when the solvent melts, the salt dissociates. The pH inside the microcapsule lowers, the dye becomes protonated, and its lactone ring opens, and its absorption spectrum shifts drastically. Therefore, it becomes deeply violet in the case deeply violet, not violent. In this case, the apparent thermochromism is in fact halochromism. The dyes most commonly used are spirolactone. There's a bunch of acids, blah blah, changing the dye molecule between its leucoform to its protonated color form. Stronger acids will make the change irreversible. Leukodyes have less accurate temperature response than liquid crystals. They are suitable for general indicators of approximate temperature, too cool or too hot or about okay, or for various novelty items. They are usually used in combination with some other pigment, producing a color change between the color of the base pigment and the color of the pigment combined with the color of the non-leuco form of the leukodye. Organic leukodyes are available for temperature ranges between about -5°C, that is 23 Fahrenheit, and 60°C, which is 140 Fahrenheit. A wide range of colors, and color change usually happens at 3°C or 5.4 Fahrenheit intervals. Leukodyes are used in applications where temperature response accuracy is not critical. For example, novelties such as bath toys, flying discs, and the approximate temperature indicators of microwave heated foods. Microencapsulated allows their use in a wide range of materials and products. The size of the microcapsules typically ranges to... That's a thing that I don't know how to pronounce, but it's a tiny measurement, which requires some adjustments to printing and manufacturing processes. An application of leukodyes is in the Duracell battery. Yep, that it is. The little indicator on the side to tell you whether it still has power. A layer of the leukodye is applied on a resistive strip to indicate its heating, thus gauging the amount of current the battery is able to supply. The strip is triangular shaped, changing its resistance along its length, therefore heating up a proportionally long segment with the amount of current flowing through it. The length of the segment above the threshold temperature for the leukodye then becomes colored. Exposure to ultraviolet radiation, solvents, and high temperatures reduce the lifespan of leukodyes. High temperatures usually cause irreversible damage to leukodyes. That explains why I ruined my t-shirts in the dryer. A time-limited exposure of some types to about 250°C, 482 Fahrenheit is allowed during manufacturing, but not over and over again in the dryer. Thermochromic paints use liquid crystals or Leukodyes technology. After absorbing a certain amount of light or heat, the crystallic or molecular structure of the pigment reversibly changes in such a way that it absorbs and emits light at a different wavelength than at lower temperatures. Thermochromic paints are seen quite often as a coating on coffee mugs, whereby once hot coffee is poured into the mug, the thermochromic paint absorbs the heat and becomes colored or transparent, therefore changing the appearance of the mug. I'm sure we've all seen these at some point or another. You put your hot coffee or your hot tea into the mug and it changes. These are known as magic mugs, or heat-changing mugs. Another common example is the use of a Leukodyes in spoons used in ice cream parlors and frozen yogurt shops. Once dipped into the cold dessert, part of the spoon appears to change color. Papers. Thermochromic papers are used for thermal printers. One example is a paper impregnated with a solid mixture of the fluorine dye with octosiliconic acid. This mixture is stable in a solid phase. However, when the octosiliconic acid is melted, the dye undergoes a chemical reaction in the liquid phase and assumes the protonated colored form. This state is then conserved when the matrix solidifies again. If the cooling process is fast enough, a leucoform is more stable in lower temperatures and solid phase and records on thermochromic papers. The records on thermochromic paper slowly fade out over years. Well, that's interesting. Polymers. Thermochromism can appear in thermoplastics, duroplastic gels, and any kind of coating. Well, that kind of makes sense. But my takeaway here is that thermochromism, just think about the word thermo meaning the temperature, and chromism meaning color. This just means anything changed by hot or cold. So, like if you get children's toys that are out in the yard, like those little Tykes cars or those little plastic slides that are made out of plastic, once they sit out in the sun and the heat and the cold for so long and they start to change color, it's that kind of thing. So a thermochromic doesn't necessarily mean it's just for liquid crystals. It's for anything that will change color with heat or cold. Furthermore, from the physical point of view, the origin of the thermochromic effect can be multifarious, so it can come from changes of light, reflection, absorption, and or scattering properties with temperature. That's what I just said. The application of thermochromic polymers for adaptive solar protection is of great interest. A function by design strategy. Example, applied for the development of non-toxic thermochromic polymers has come into focus in the last decade. Inks. Thermochromic inks are dyes are temperature-sensitive compounds developed in the 1970s that temporarily change color with exposure to heat. They come in two forms, liquid crystals and Leukodyes. Leukodyes are easier to work with and allow for a greater range of applications. These applications include flat thermometers, battery testers, clothing, and indicators on bottles of maple syrup. Bottles of maple syrup? Well, that's interesting. I'd like to hear if anybody has any bottles of maple syrup with that on it. That change color when the syrup is warm. The thermometers are often used on the exterior of aquariums or to obtain body temperature via the forehead. Coors Light uses thermochromic ink on its cans now, changing from white to blue to indicate the can is cold. Well, I don't really drink a lot of beer, so I don't know, but that's interesting. On that. Get a 12-pack and see. Inorganic materials. Virtually all inorganic compounds are thermochromic to some extent. Most examples, however, involve only subtle changes in color. For example, titanium dioxide, zinc sulfide, and zinc oxide are white at room temperature, but when heated change to yellow. Similarly, indium-3 oxide is yellow and darkens to yellow-brown when heated. Lead-2 oxide exhibits a similar color change on heating. The color change is linked to changes in the electronic properties, that is, energy levels, populations of these materials. More dramatic examples of thermochromism are found in materials that undergo phase transition or exhibit charge transfer bands near the visible region. Examples include cuprous mercury iodide undergoes a phase transition at 67°C, reversibly changing from a bright red solid material at low temperature to a dark brown solid at high temperature. While intermediate red-purple states, the colors are intense and seem to be caused by Cu1Hd2 charge transfer complexes. Silver mercury iodide is yellow at low temperatures and orange at about 47 to 51 C. Mercury 2 iodide is a crystalline material which at 126 C undergoes reversible phase transition from red alpha phase to pale yellow beta phase. And let's see. Vanadium oxide has been investigated for use as a spectrally selective window coating to block infrared transmissions and reduce the loss of building interior heat through windows. This material behaves like a semiconductor at low temperatures, allowing more transmission, and like a conductor at higher temperatures, providing much greater reflectivity. Phase change between transparent semiconductive and reflective conductive phases occurs at 68 C. Doping the material with 1.9% tungsten lowers the transition temperature to 29 C. Well, that's interesting. Let's see, that's all it has to say about thermochromism. Just things that change color with temperature. Okay. Okay, now let's see if we can glean what a liquid crystal is from the liquid crystal article. For some reason, they're not always real clear in these articles about what a thing actually is. Anyway, here we go. Liquid crystals, which we will also be referring to as LC, is a state of matter that has properties between those of conventional liquids and those of solid crystals. For instance, a liquid crystal may flow like a liquid, but its molecules may be oriented in a crystal-like way. There are many different types of liquid crystal phases, which can be distinguished by their different optical properties such as textures. The contrasting areas in the textures correspond to the domains where the liquid crystal molecules were oriented in different directions. Within a domain, however, the molecules are well ordered. Liquid crystal materials may not always be in liquid crystal state of matter, just as water may turn into ice or water vapor. Okay. So, liquid crystals aren't crystals like you imagine holding a quartz crystal. Tiny, tiny crystals, like molecule size. Okay, liquid crystals can be divided into thermotropic, lyotropic, and metallotropic phases. The thermotropic and lyotropic liquid crystals consist mostly of organic molecules, although a few minerals are also known. Thermotropic liquid crystals exhibit a phase transition into the liquid crystal phase as temperature is changed. Lyotropic liquid crystals exhibit phase transitions as a function of both temperature and concentration of the liquid crystal molecules in a solid, typically water. Metallotropic liquid crystals are composed of both organic and inorganic molecules. Their liquid crystal transition depends not only on the temperature and concentration, but also on the inorganic-organic composition ratio. Examples of liquid crystals can be found both in the natural world and in technological applications. Widespread liquid crystal displays use liquid crystals. Lyotropic liquid crystalline phases are abundant in living systems but can also be found in the mineral world. For example, many proteins and cell membranes are liquid crystals. Other well-known examples of liquid crystals are solutions of soap and various related detergents, as well as the tobacco mosaic virus. Okay, tobacco mosaic virus is a liquid crystal. Okay, and some clays. The history. In 1888, Austrian botanical physiologist Friedrich Reinitzer, working at the Karl Ferdinand Universität, examined the physiochemical properties of various derivatives of cholesterol, which now belong to the class of materials known as cholesterol liquid crystals. Previously, other researchers had observed distinct color effects when cooling cholesterol derivatives just above the freezing point, but had not associated it with a new phenomenon. Reinitzer perceived that color changes in the derivative cholesterol benzoate were not the most peculiar feature. Okay. He found that cholesterol benzoate does not melt in the same manner as other compounds, but has two melting points. At 145.5 Celsius, that is 293.9 Fahrenheit, it melts into a cloudy liquid. And at 178.5 Celsius, that is 353.3 Fahrenheit, it melts again, and the cloudy liquid becomes clear. The phenomenon is reversible. Seeking help from a physicist on March 14, 1888, he wrote to Otto Lehmann, at the time a Privatdozent in Aachen. I'm pretty sure that's a title, but I don't know what it is. They exchanged letters and samples. Lehmann examined the intermediate cloudy fluid and reported seeing crystal lights. Not the drink. Renitzer's Viennese colleague von Zephyrovich also indicated that the intermediate fluid was crystalline. The exchange of letters with Lehmann ended on April 24th with many questions unanswered. Reinitzer presented his results with credits to Lehmann and von Zephyrovich at a meeting at the Vienna Chemical Society on May 3, 1888. By that time, Reinitzer had discovered that the described three important features of cholesteric liquid crystals, the name coined by Otto Lehmann in 1904, the existence of two melting points, the reflection of circularly polarized light, and the ability to rotate the polarization direction of light. After his accidental discovery, Reinitzer did not pursue studying liquid crystals further. The research was continued by Lehmann, who realized that he had encountered a new phenomenon and was in a position to investigate it. In his postdoctoral years, he had acquired expertise in crystallography and microscopy. Lehmann started a systematic study, first of cholesterol benzoate, and then of related compounds which exhibited the double melting phenomenon. He was able to make observations in polarized light, and his microscope was equipped with a hot stage, sample holder equipped with a heater, enabling a high temperature observations. The intermediate cloudy phase clearly sustained flow, but other features, particularly the signature under a microscope, convinced Lehmann that he was dealing with a solid. But it melted and it was still a solid, so that's interesting. By the end of August 1889, he had published his results in I'll try. Zeitschrift für Psychologische Chemie. Close enough. Lehmann's work was continued and significantly expanded by German chemist Daniel Vorlander, who from the beginning of the 20th century until he retired in 1935 had synthesized most of the liquid crystals known. However, liquid crystals were not popular among scientists, and the material remained pure scientific curiosity for about 80 years. Okay, now hold up with all this crazy weird definitions. All I really want to know is what makes liquid crystals, and Wikipedia isn't giving me that answer. So I had to sneak out of Wikipedia over here to PC Magazine, which I'm told is old as the hills, or at least computers. And they have a encyclopedia, and it says a liquid crystal is a state of matter between liquid and a solid, known as a mesophase. They change shape like a fluid, but have the molecular alignment characteristics of a solid crystal. And that's all I really wanted to know. What makes it a crystal? And right there it is. And Wikipedia couldn't give that sentence anywhere. Molecular alignment characteristics of a solid crystal. Liquid crystals are composed of organic rod-shaped molecules that align in parallel, and the common types used in electronic displays are pneumatic, cholesteric, and smectic. They are used in LCD displays all the time. Your monitors, your phones, your everything that lights up and you look at. And they have just a few sentences on the history here of when it was discovered, unlike Wikipedia's long drawn-out insanity. It says, discovered in the 19th century, in 1888, liquid crystals were identified by Austrian botanist Friedrich Reinitzer and German physicist Otto Lehmann studying the cholesterol in carrots using a temperature-controlled polarizing microscope. They noticed that the light passing through the carrot compound, later known as cholesterol benzoate, exhibited the refraction effect of a solid crystal when heat was applied. By 1907, Germany-based Merck was selling the liquid and flowing crystal chemical. And there you have it. the molecules in liquid crystals behave like the molecules in crystals and how they align. That's the end of this episode. I hope you found it informative and interesting and a fun thing to make. And I will see you next time. Thank you.